Hey everyone. All right, welcome to our quadratic functions unit. Now, some teachers, some schools may look at quadratics and just give you one big unit. We have split this into two units. We're going to have one unit on quadratic functions and then one unit on quadratic equations. Um, it's the same whether you do it as one big unit or two little units. But just if you're coming from a school where it is just called quadratics, think of this as the first half of that unit. But for us, it's going to be its own unit, and so on YouTube it'll be its own playlist. Okay. Now, the purpose of today is to do a unit opener. Now, when we do unit openers, essentially, I'm going to walk you through a bunch of things, and I'm going to tell you a bunch of stuff on what's coming up. Okay, so I might introduce words that you've never heard before, and I might sound like you should know what I'm talking about. You shouldn't, okay? So don't let that stress you out. It's just meant to kind of, it's like the trailer to a really, really good movie, okay? It's meant to kind of get your brain thinking about some of these words. Please do not watch this video and then leave stressed because of all these words I said. The whole unit is going to unpack every word I say today, okay? So this is just meant as an introduction, just to get the brain juices flowing and to get you to see kind of where we're headed, okay? So on that note, let's get going. It's going to be super fun. Here is the first example I want to do with you, and I'm just going to hide my head for just 1 second so that we can read the question together. Below is a table that shows the height in feet of a snowball being thrown with respect to time in seconds. Plot this data on the grid below and answer the following questions. So you have a grid to go with this data. And what I want you to remember is, hey, we've got a table of values here. Each row becomes a point that we can plot, right? So that would be the point bracket 0, comma 1, and this would be the point 1, comma 5.5, okay? So then on a graph, you'd have 0, 1, and 1, 5.5, and you just want to see where all these dots are going to take you. So give a pause to me, shut me up for a couple minutes, you plot all of this data, and then come back and look at my picture, okay? All right, welcome back. I hope you had fun. Here is the picture that you should be looking at the moment. Yeah, and so we can see this kind of general shape that really in math we haven't talked much about. We did not deal with this shape in grade 10. In grade 10, we dealt a lot with a function that might look like this, okay? And that became a straight line, and that was called a linear function, okay? But when we graphed it, it would look something like this, nice and steep there, and a y-intercept at 5, okay? But every line we looked at gave us the same shape. It was the shape of a line, okay? This is called a degree 1 polynomial because the exponent on this x right here, there isn't one there. That means it would be a 1, okay? This, friends, is called a degree 2 polynomial. So now on that front x term, we're actually going to end up seeing a square, okay? And when we see a square, that's called a quadratic formula, okay? Remember I said I was going to introduce a bunch of words to you, right? That's called a quadratic formula, and it gives this general shape, and this general shape is called a parabola, okay? Parabola. Okay, awesome. So, yeah, I'm gonna clear that. And what I'm gonna do is now that we have kind of that general shape, I'm gonna ask you the first question, and then I'm gonna shove this picture up to the left, top left corner there, so that we can talk about some more questions. But the first one we wanna talk about first is this. Should the data points be connected or not? Should this be a continuous or discontinuous graph? In grade 10, we would have called that continuous or discrete, okay? Right now, I have it as discrete. I have it as a bunch of points because those are the points I plotted from the table, okay? But given the context of this question, I'm throwing a snowball. So if I think about the fact that I'm throwing a snowball, yes, I dropped my pen there, sorry. I have, 2 seconds. I know that at 2 seconds, I'm 10 feet high. But to go from 1 second to 2 seconds, I passed through every possible point between 1 and 2. Okay. And to go from 5.5 feet high to 10 feet high, I passed through every point, or I didn't, the ball did, but you know what I mean. The ball passed through every point between 5.5 and 10, okay? So the distance of the ball, the height, is a continuous item, and time is also a continuous item. We can be in between these data points. And so because of that, given the context of this question, yes, we should actually join those dots together. And so we're actually going to get a shape, if I join all that together, that looks more like this. Okay, so now what I'm going to do is I'm going to shove this up to the top left, and that way I can answer the question that I just asked you. So here's the answer. The dots should be connected to one another because you have moments and heights that are in between the ones given. The data is continuous. Okay, awesome. Do you think the graph table of values should continue or stop? Now, this is a great question. If I think about this as a mathematical shape, we know that this mathematical shape is going to continue down in that direction forever and continue down in that direction forever. So in that sense, in both directions, it's just going to go down to infinity, head to the left, head to the right, mathematically, okay? But in the context of this question, a lot of that has no meaning, okay? So when we're asked a contextual question, we need to look at what is meaningful given the context, okay? Here I have released the ball is flying into the air, and then the ball is dropping. Well, right here, the ball hits the ground. Everything after that is kind of meaningless according to the context of this question, right? The ball is not going to now burrow into the ground and keep going, nor am I able to go back in time and say that the ball came out of the ground into my hand for me to throw it, right? Like none of that makes any sense. So all of this is kind of meaningless to the context of the question, and then all of this would be kind of meaningless to the context of the question as well. That leads us into talking about domain and range, but we'll get there in 1 second. As far as this question goes, what I'm saying is, yes, it should stop, okay? So, stop. Once the snowball hits the ground, the graph becomes meaningless in its context. The snowball is not going to burrow into the ground, okay? Okay, does this graph have a maximum or a minimum? And what do you think that value is? Well, it looks like we have a maximum. Maximum means the highest point possible. Looks like we have a maximum right there, okay? Now, you may think, oh, I might be guessing at what that point is, but if I come down here, I'm very, very confident that that's at 6. And actually, if I went back to my table, 6 was actually listed. I believe it was 18. So you can go back and check me on that. Okay, so the graph has a maximum. It looks like the value of the maximum occurs at 6 seconds. Reading this information from our table, we can say that the maximum then would be 18 feet. Okay. Right. Awesome. What is the y-intercept, and what does this value represent in the context? Well, we know from grade 10, the y-intercept is when I hit the y-axis, okay? It's also when the value of x is 0. Now, because x in this particular context is time, that means at time 0. So time 0 would be right when I release the snowball from my hand, okay? So I can read that off my table. I did have the point where x was 0 on my table, and it was a height of 1. So the snowball is actually being released 1 foot off the ground. So if I'm throwing this, it's probably like an underhand throw. And so when I release, my hand is closer to the ground. Or maybe I have a snowball throwing machine that I don't know, positioned on the ground. But whatever, the snowball is 1 foot high at the time it's launched, okay? Okay, so remember, I know you're probably going to think I've reminded you of this thousands of times by the time this course is done, but it's super important from a guy who marks diploma exams and sees silly mistakes kids make all the time. If you are asked for an intercept has to be written as a coordinate. Okay, you can't say y equals 1. Y equals 1 is like a horizontal line. Okay. As well, you can't say this. That is not a coordinate point. Okay. I see that a lot from kids, and I'm not quite sure why I see that. That's a string of numbers. It's not a coordinate point until you put curved brackets around that. So just be careful in your communication. That's super, super important. Okay. All right, awesome. What do you think the x-intercept will be? What does this value represent in context? Now, actually, I want to have a couple conversations here. First, notice I said the x-intercept, meaning there was only one. Actually, there's two. You can see one right here, and you can see one right here. The only one I actually care about is this one, and that's why I did not pluralize this word. This one technically is not there, right? Because it's not meaningful in the context of the question. It involves a negative time value, and we know that the graph only actually started right here. So because of the context of this question, we would consider this to only have one x-intercept over here, okay? So I'm going to say, and it's just, what, a little after 12. So let's call that 12.1. Okay, so I'm going to say the meaningful x-intercept occurs just after 12 seconds, approximately 12.1 seconds. This is the time it hits the ground. So it represents the total time the ball was in the air. Okay, so all along here, that represents the time it took from the time the ball was launched to the time the ball hit the ground, about 12.1 seconds. Okay, awesome. Okay, sorry, I can't get my mouse to work here. Let's try that. Okay, what is happening at 6 seconds? Okay, so at 6 seconds, we actually were already talking about 6 seconds, but we can see it right here. At 6 seconds, I have that height of 18, and I've reached my maximum point, okay? That point, just to start throwing some words at you, that point is called the vertex, okay? The vertex is where I change direction on a parabola. Either I'm coming up and then changing to going down, or I'm going down and changing to going up, okay? Okay. So what's happening at 6 seconds? At 6 seconds, the ball has reached its maximum point and will now begin to fall back to the ground, okay? Okay, how long is the snowball above 10 feet? Well, that's a y value, right? 10 feet. So let's just put that in right here. And here's what I want you to notice, okay? At this point right here, this is the point that I begin to be above 10 feet at 2 seconds. Then this is the point that I stop being above 10 feet. So from the 2-second mark all the way to the 10-second mark, the ball was above 10 feet. Okay, so that is 8 seconds altogether. I just subtract those two x values. Okay, so the ball is above 10 feet starting at the 2-second mark and going until the 10-second mark. So the ball is above 10 feet for 8 seconds in total. Okay? All right, great. That was our first kind of contextual question. Now we're going to switch the context and kind of do similar questions, but in a slightly different context. So I'm going to hide my face here so I can read the question to you. The following graph represents a person's height in feet and time in seconds as they are on a ride at Calway Park. Okay, do you think the graph and table of values should continue or stop? Again, this should stop because we're talking about a ride, right? Rides don't just go on for eternity. There is a start to the ride and there is an end to the ride, okay? If you're really good at interpreting graphs, you'll look at this particular graph and feel like this is kind of a boring ride because you started at 9 feet tall, right? And you dropped down to what? 1 feet. Let's just interpret this for a second. You dropped down to 1 foot, in 4 seconds, and then back up to 9 feet in another 4 seconds. Okay, so how tall is 9 feet? Your ceiling of your house, if you're watching this in your house, is somewhere between 7 feet and 9 feet. okay, just to give you kind of a perspective of how tall this is. So, maybe this is a kiddie ride at Callaway Park. Nothing too stressful or anything. But yes, the value should stop. That didn't really have anything to do with the question, so I should probably answer the question. The graph should stop. The ride does not continue forever. There's a distinct starting point and a distinct ending point to the ride. Okay. At what height did the rider get on the ride? Well, actually, as I was interpreting this graph, I've kind of answered those questions. I started at 9 feet in height. So the rider got on the ride at a height of 9 feet. Okay. What is the minimum height of the rider? I've actually already written it there. And when does this happen? So the minimum height is 1 foot. Okay. And then when does that happen? It happens at 4 seconds. Just reading that right off my graph, I can see the minimum here of 1 foot, and I can see that it happens at 4 seconds. Okay. Awesome. When is the height of the rider? Is the height of the rider after 2 seconds? So I head over to that 2-second mark right there, and then I can see the height of the rider right here is 3 seconds. Okay. So at 2 seconds, the height of the rider is 3 seconds. Yay for us. See, this isn't bad. How long is the rider beneath a height of 3 feet? So again, I want to put on that 3-foot line. Okay. And then I can see that at this moment, just getting a new color here. At this moment, I begin to be below 3 feet. At this moment, I stop being below 3 feet. So I'm going from 2 to 6. So that would be 4 seconds altogether. Okay, so the rider is beneath a height of 3 feet from 2 seconds to 6 seconds. So 4 seconds in total. Awesome. You got this. What is the domain of this graph? Okay, so domain is a description of all the values that x can be, all the values that your input can be. So when we're trying to figure out domain, I look for my lowest x value, reading from left to right, right? So my lowest x value is 0, and my highest x value, that was not a great line, sorry. My highest x value is 8, okay? So I would say the domain is from 0 to 8. Now, if you remember this from grade 10, there's very specific rules around how to write domain and range, okay? So if we're using set builder notation, this is what that would look like. We have a squiggly bracket, and then we write an X and then a straight line. So if we were to say this out loud, we would say all the values of X such that or where 0 is less than or equal to x, which is less than or equal to 8. So that's saying 0 or x is in between 0 and 8. And then, comma, x is a member of the reals. That tells us this x is a member of the reals, tells us we're dealing with continuous data. Okay. Awesome possum. Okay, what is the range of this graph? So now we're looking for the y values. We're going to read from the bottom to the top. So I can see that my lowest y value is at 1, and my highest y value is at 9. Okay, so the range is from 1 to 9. And I'm going to write this just like I did the domain, except instead of writing x, I'm going to write y's. So all the values of y such that 1 is less than or equal to y is less than or equal to 9, comma, y is a member of the reals. So that is saying y is in between 1 and 9 and can be any number in between 1 and 9. Right, awesome. Next up, I'm just going to hide my head here for a quick sec. A quadratic function can be written in many forms. One form looks like this: y equals 0.25 times x plus 4 times x minus 6. Use this function to answer the following questions. Okay, so first of all, we are going to complete a table of values and draw the corresponding graph. So to complete the table of values, I gave you some x values that we're interested in. So you're going to plug in -4 for x here and here, see what you get out, plug 0 in, see what you get out, plug 1 in, see what you get out, and plug 6 in, see what you get out. Okay, so pause me and do that. Okay, now let's compare our answers together. You should have -4, the y value that goes with -4 was 0. You should have 0, comma, -6, and then 1, -6.25, and 6, comma, 0, if we're thinking about these as coordinate points. So now you have a grid in your book. I want you to go ahead and graph those 4 points, see if you can get a general shape going. Or you paused me, right? Okay, and this is what your graph should look like. Okay, so again, we have that same sort of shape. Again, this shape is called a parabola, and it's made by a quadratic function. Now, while we're looking at this form, let me just say a quadratic function has an x squared in it. Now, you may look at this and say, oh, there's no x squared here. Yes, there is, because when you multiply x by x together, you would have an x squared there, okay? Okay, so let's answer some questions around this graph. I'm just going to move this graph up to the top, and then I'll have some questions on the bottom. So, should the data points be connected, and why? Now, yes, the data points should be connected. I drew them connected right away, but why did I do that? The reason I did that is because I had an equation. And as soon as you have an equation, you can put anything you want in for x, right? You could put 1 in, you could put 1.2 in, you could put 1.782824 in. So even though you're generating dots, you know that those dots are showing you a pattern where you can connect those dots because anything in between those dots still exists. Okay, so yes, they should. Because we have been given an equation, we can put anything we want in for x and get out a corresponding y. The data is continuous. Okay. State the domain and range. Well, the domain is going to be real, so all the values of x such that x is a member of the reals. The range, I can't be anything I want on the range because I have a bottom to this graph. And the bottom is at -6.125. I got that backwards, sorry. -6.25. You have that right on your table if you just want to reference it. Okay, so domain is all the values of x such that x is a member of the reals. Range, all the values of y such that y is greater than or equal to -6.25 and y is a member of the reals. When you are asked a question like this where it says state the domain and range, make sure you've labeled which one is the domain and which one is the range. Don't assume because you've written X that you've stated that you're saying the domain, okay? If I am marking you and you don't state the domain, it makes me as a teacher think, huh, do you know that the domain involves X and the range involves Y? Or do you just know these are the two of them, but I don't really know which one's which, okay? So make sure you're labeling which one is the domain and which one is the range so that your communication is like super awesome, amazing. Okay, what are the x-intercepts? Could you determine these easily from the function somehow? Well, if we look at this, we see an x-intercept here at -4 and here at 6. Okay, so remember, I said this already, but if you're talking about intercepts, you have to state those as coordinate points. So the x-intercepts occur at bracket -4, comma 0 bracket and bracket 6, comma 0 bracket. These seem to be connected to the factors in the original equation. If we set each factor equal to 0, we would have the x-intercepts, right? I have a factor, let me just get my ink back on here. I have a factor of x plus 4. If I said that equals 0, I would get x equals -4, and that is this guy right there. Then I had a factor of x minus 6. If I set that equal to 0, I get x equals 6, and I see that guy right there. Okay, now you may look at that and say, how was I supposed to know that? You weren't. Remember, this is just an opener. We're going to dive into these things more as we go. This is not meant to stress you. It's meant to get you super excited about what we're about to do in this chapter. It's going to be so fun. What number is exactly in the middle of the x-intercepts? Now, if I want something in the middle, I take the average. So we just talked about the fact that this was at -4, this is at 6, -4 plus 6 divided by 2. That would be taking the average, right? What's that? Negative 4 plus 6 is 2. 2 divided by 2 is 1. So right in the middle, I'm just going to draw a line there at x equals 1. Hey, take a look at that. That hits the vertex, the change of direction. Okay. Now, if you want some vocab, because I know you're dying for some vocab, that vertical line I just drew is called the axis of symmetry. Yeah. Okay. Sorry, my hesitation wasn't the math. My hesitation was I was staring at symmetry, wondering if there's one M or two M's. And I still am not sure. So if I spelled that wrong, please forgive me. Okay. So we have right in the middle of the x-intercepts, that occurs at x equals 1. This is the average of negative 4 and 6. It also tells us where the vertex is located. Okay. All right, what is the y-intercept and how would we determine that algebraically? Well, I can see it here. The y-intercept is at 0, negative 6. I can also reference that from my table, right? I had the point 0, negative 6 in my table. But how did I get the negative 6 in the first place? I did do that algebraically. I plugged in 0 for x, okay? So anytime you want a y-intercept, you're going to plug 0 in for x and determine what the y value is. So the y-intercept is bracket 0, negative 6, bracket. To determine this, we can plug in 0 for x and solve for y, okay? Awesome. What are the coordinates of the vertex? So I kind of have already talked a little bit about the vertex. Could you determine these easily from the function somehow? Well, for this guy, the coordinates of the vertex is at bracket 1, negative 6.25 bracket. Don't forget your brackets there. It's not a coordinate if you don't have brackets, okay? We knew the x value had to be the average of the x-intercepts, and we already figured that one out, right? So we took that negative 4, added 6, divided by 2, and we got the x value at the vertex is 1. Then we can just plug 1 into the equation, substitute x for 1, and get out the corresponding y value, and that would give us the negative 6.25. Okay. Would you say the graph opens up or down? The graph opens up. Okay, good. So that was one type of form that we're going to deal with over the next week or so. Another type of form looks like this. Okay, again, I'm just going to hide my head for just 1 sec. Another form would be something that looks like this. Y equals negative 0.5 bracket x minus 2 bracket all squared plus 3. Use this function to answer the following questions. Okay, so use the table of values. This time we already gave you the table of values. We didn't ask you to generate it, but you're going to draw the corresponding graph. So make sure you pause me, get these points, see if you can figure out the general look of this graph. Okay, welcome back. You should have a picture that looks something like this. Now, we still have that general shape of a parabola, okay? It is still generated by a quadratic. Remember I said a quadratic had an x squared in it. This guy here is where my x squared is going to come from, because that x minus 2 all squared, well, that's x minus 2 times x minus 2. What's x times x? That's going to give me that x squared point, okay? Okay, so just like I did with the last example, I'm now going to push this graph up to the top corner here, and we'll answer some questions together. Okay, so the first question, should the data points be connected or not? Do you know what? That's the exact same answer the last time I asked you. This time I'm given an equation. It's a different form, but I'm given an equation. When I'm given an equation, I can definitely connect those dots together. So yes, they should. Because we have been given an equation, we can put anything we want in for x and get out a corresponding value for y. The data is continuous, okay? Does the function have a maximum or minimum, and what is the value? This time the function has a maximum, it's got a top, and it looks like that value is sitting at 3. Okay, so the function, oh, that's a mistake. You know what? I copied that. I copied and pasted from the other example. I apologize. That's a maximum. The function has a maximum at 3. Okay, maximum at 3. Okay. State the domain and range. The domain will be real again, because this graph is going to go forever to the left and forever to the right. Okay. As far as the range goes, this time I have a top, so I can be everything less than that maximum number, which is 3. So domain is x is a member of the reals, and then the range is y, all the values of y such that y is less than or equal to 3, and then y is also a member of the reals. Okay. What are the x-intercepts? Could we determine these easily from the function somehow? Now, this one, I can figure out the x-intercepts. They're not quite as easy to read from my graph, okay? But they do happen to be at negative 0.5 and 4.5. These are not seen as easily in this form. If you remember back to 10C when we talked about the different forms of a linear function, each form was friendlier for something. Do you know what I mean? They told us something. So this particular form that we're playing with right now doesn't show us the x-intercepts as easy as the first form did. Okay, but doesn't mean we can't solve it. All we'd have to do is plug 0 in for y and then solve for x. Okay. Okay, what number is exactly in the middle of the x-intercepts? Again, it would be the average. So I'm going to take that negative 0.5 and that 4.5, add them together. And if I added them together, I get 4, and then divide by 2, and I would get 2. So the middle of the x-intercepts occurs at x equals 2. This is the average of negative 0.5 and 4.5. It also tells us where the vertex is located. And if I wanted to show you again, I could write that vertical line right at x equals 2. And that would be my axis of symmetry. Okay. Cool. What is the y-intercept and how would you determine this algebraically? Well, of course, we know how to do that. We would plug 0 in for x and solve for y. Okay, so if I plug 0 in for x, I'm going to get negative 2 squared, which is 4. Multiply that by negative 0.5. So that'd be negative 2. And then negative 2 plus 3 will give me 1. And I can see that right here as well, that it passes at 0, comma 1. So the y-intercept is bracket 0, comma 1. To determine this, we plug in 0 for x and solve for y. Okay. All right, what are the coordinates of the vertex? Well, we know this now. The coordinates of the vertex are 2, comma 3. Now, the next question is, could we determine this easily from the function somehow? Again, would I expect you to come up with this right on your own right now? Absolutely not, but take a look at this. There's my 3, and there's my 2, okay? Right off the bat, you're going to hear me say this 1,000 times, but right off the bat, notice that it says x minus whatever that number is, okay? That's just something to get in your head right away. But this is actually called the vertex form of an equation because it tells us the vertex, okay? Again, I am just introducing things to you right now. We are going to slowly go through all of these things over the next 5, 6 lessons, okay? Don't stress if you're not catching everything right now. I'm just kind of giving you the trailer to the best movie ever, okay? The coordinates of the vertex is bracket 2, comma 3. We can see this in the equation above. The x value comes from what is being subtracted from x, and the y value is what is being added at the end. All right, would you say this graph opens up or down? It opens down. Now, the next part of this says, how could you tell? Well, again, I don't know if you've been looking for patterns or anything, but the difference here is this front number. If that front number is negative, the graph will open down. If that front number is positive, the graph will open up. And that front number is called a leading coefficient. Okay. Okay. Just get my answer there. The graph opens down. We know this because the number in front of the equation is negative. Okay. All right, awesome. Now, let's just go through a few words probably that I mentioned over the last few minutes here. But if not, they're just words that you do want to kind of start getting in the forefront of your mind as we move forward. Okay, so intercept is where the function crosses an axis. We can have an x-intercept or we can have a y-intercept. Okay, minimum or maximum would be the highest or lowest y value for a given function, highest being the maximum, lowest being the minimum. Vertex, the point where the graph changes from increasing to decreasing or from decreasing to increasing. So where the graph is changing direction. Leading coefficient, the number at the beginning. If it is positive, the quadratic will open up. If it is negative, the quadratic will open down. Hey, look at that. I did spell symmetry right. There are two M's in symmetry. Axis of symmetry, the vertical line that passes through the center of the parabola. And then domain and range, descriptions that state the allowable values for x and y, where the function can exist. Okay, and then domain speaks about the x values or your inputs, and range speaks of the y values or your outputs. Okay. All right, some basic function terminology. We are going to fill in some blanks here. I'll hide my head for just one quick second. Relation, a rule that associates the elements of one set with the elements of another set. Relations can be represented by words, by something pairs, coordinate pairs or ordered pairs. And then a table of values, or graphs, or equations. Okay, all of those are ways of representing relations. A function. A function is a type of relation in which for every valid input is your x value, there is only one possible output, and output is your y value. Okay, the vertical line test is an easy way to determine if a relation is a function. If every vertical line can be drawn intersecting the graph only once, then the graph is a function. If not, the graph is a relation. Okay, so all of this terminology you would have talked about in grade 10. So me walking you through it right now is just kind of getting it back into the forefront of your mind, making sure you remember this stuff. If you don't remember this, friends, don't worry. Check out some of my 10C videos. Just kind of look up function, look up relation on my YouTube channel, and you'll find the right video, and you can kind of review and make sure your mind is nice and fresh. Okay. Okay, function notation says f of x. Now, it's said as f at x or f of x. And what it is really is we have this function f, and then it refers to the inputs x. Okay, so it refers to the value of the output. F of x is the output with x being the input. So if I was to say f of 1, what I'm really saying there is what's the value of the output when your input is 1. Okay, because I replaced x with 1 and x is my input. Okay, so f of 1 speaks of the y value when x is 1. Okay, the domain, the set of all independent variables, otherwise known as your x values of a function or relation. The range, the set of all dependent variables or your y values of a function or relation. Then we have the horizontal intercept and the vertical intercept. Horizontal intercept is known as the x-intercept. It's the point at which a graph intersects the x-axis. X-intercepts have the form bracket, x comma 0 bracket, not x equals a. So you don't say x equals something when you're asked for an intercept. You write it as a coordinate point. Okay. Same with vertical intercept, also known as the y-intercept. It's the point at which a graph intersects the y-axis. Okay. And then y-intercepts have the form bracket 0 comma y. They're written as a coordinate point, not y equals some number. Okay. Awesome. Okay, so let's just go through a couple of graphs and make sure we can determine them properly. I'll hide my head for just 1 second for this first question. Determine the domain and range. Well, the domain is going to be real and the range is going to be greater than -3. But I do just want to have a quick conversation there. Just a reminder about the standard for computer-drawn graphs. If computer-drawn graphs go right to the edge of the window that they're showing you, you can assume that means they go on forever, okay? If you have a hand-drawn graph, if you're drawing a graph, you should always have arrowheads on it, okay? But a computer-drawn graph doesn't need arrowheads. If it goes off the page, off the little window of the graph, then it does go on forever, okay? Okay, determine if the graph is a relation or a function. Well, this is a function. Now, it passes the vertical line test, but that's not actually what I would want you to say. I would want you to tell me the definition of a function if I ask you to tell me why it's a function. So the graph is a function. For every value of x, there is a single value of y. Okay, that is what the definition of a function is. Okay, same questions here. I'll just hide my head for the first one. Determine the domain and range. For this one, they're both real. X is a member of the reals and Y is a member of the reals. I'm going to go up and to the right forever, and I'm going to go down and to the left forever. Okay, is this graph a function or a relation? Yes, it is a function. Again, same reason. For every x, there is a single y. Okay, the graph is a function. For every value of x, there is a single value of y. Okay, next one. Determine the domain and range. Now this guy, we have to kind of plot this out because I have a distinct start and stop. So if I'm looking at the domain, I'm going to go from -3 to 5. Okay, then if I'm looking at the range, I'm going to go from -4 to 4. Okay, so the domain will go from -3 to 5. The range will go from -4 to 4. Looking something like that. Okay. Determine if the graph is a relation or a function. Again, it is a function, passes the vertical line test, but my reason is for every value of x, there is a single value of y. Okay. Yay. Okay, awesome. Sketch the graph. I'll just hide again. Sketch the graph of a relation that is not a function. So you get to draw anything you want that doesn't pass the vertical line test. Okay, so maybe you want something like that. That's not going to work. Maybe you want, I don't know, something like that. That won't work. Maybe you want something like, see, I put a little vertical line in there. So that would not be a function. Okay. Okay. Anything like that would work fine. Okay. I put a circle in, but yeah, anything where there's more than one input for a given, sorry, there's more than one output for a given input at some point. Okay. Okay. Graphing. Recall there are 3 methods to sketch a graph. Either we can use the intercepts, we can create a table of values, or if it's a line, we can do the slope y-intercept form. Okay, so sketch the graph of the function f of x equals f -1/2 x plus 3 using one of these 3 methods. Now, what I'm going to do is I'm going to do this using slope y-intercept because I'm in slope y-intercept form anyway, right? So I know that my y-intercept is at 3. So I know I'm going to have a point at 3. And then I have a slope of -1/2. So from that point, I'm going to go down 1, right 2, down 1, whoops, down 1, right 2, down 1, right 2. Okay. And then I'm going to get a straight edge. Okay. And I'm going to connect those dots with a line. And then I'm going to make sure that, because this is a hand-drawn graph, sort of, because it's a hand-drawn graph, I'm going to put arrowheads on, okay? So in my reasoning, I'm going to state, hey, I know that the y-intercept is at 0, 3, and I know that I have a slope of -1/2, and then this is exactly what I just did, and there's our line, okay? Awesome. Okay, I'm just going to hide one more sec here. Sketch the graph of g of x equals x squared using one of the three methods. Now, this one's a little different. When things are a little different, I'm going to go to a table of values. So I'm going to create a table of values. I'm going to go to -2, -1, 0, 1, 2 for my x values, plug those in and get my y values. So -2 squared is 4, -1 squared is 1. Just remember, if you're throwing that in your calculator, -2 squared would have to be written like that, right? Because -2, it's -2 times -2. So I would have 4, 1, 0, 1, 4. Now, right away, I know this isn't linear anymore because I can see my y values change direction. My y values were going down and then they turned and went up. Okay, so I'm going to plot those and see what happens. I've got -2, 4. I've got -1, 1, 0, 1, 1, 1, and 2, 4. Okay, and then I can see that um, parabolic shape, so it's a parabola there. Okay, and that's what we're going to spend lots of time on over the next few lessons, is dealing with that shape. Okay, all right, my friends, you did it. This was our unit opener. And we've reached our last little example together. You guys have rocked this. I hope this has been helpful to kind of get your brain back in the game when it comes to some of these words around functions and function notation and domain and range. If you're stressed, though, don't worry, it's going to come back. It might take a little bit of review, and I'm happy to help you with that. But make sure, if you are stressed about it, that you do kind of get some extra review done so that you can feel really good about this as we move forward. Okay. Hey, thanks for watching. Thanks for letting me take this journey with you. I do really appreciate it. Thank you for sharing these videos with your friends and letting them know that these resources are available. I really appreciate that. And of course, thanks for subscribing to my YouTube channel. I super appreciate that. Now you got some work to do, and you know where to find me if you have any questions. And then we'll dive into lesson 2 when you're ready. Take care, guys.